Hello everyone, my name is Krati Gupta. I'm an assistant professor in a guide group of institution. In this video, we will be studying about the graph traversal technique, breadth first search. The content for this lecture will be graph traversal, breadth first search technique, breadth first search algorithm. Then we will be illustrating this algorithm with the help of example, BFS example, then a pseudocode for breadth first search technique. Graph traversal is a process of visiting all the vertices of a graph. Now how we are visiting all the vertex of a graph, the sequence in the order in which we are visiting all the vertices of the graph, on the basis of that graph traversal was classified into two types: breadth first search traversal and depth first search traversal. Breadth first search traversal is traversing all the vertices of the graph in a level by level ordering, and depth first search traversal is visiting all the vertices of a graph in a depth by depth sequence. Both the breadth first search and depth first search traversal will give rise to a spanning tree. Whenever a node is visited, it is labeled as visited and it will be added to the tree. And if the traversal got to a node X from certain node Y, then it will be viewed as that Y is a parent of X or X is a child of a Y. That is, if you are visiting a particular node A from a node B, then this B node will be the parent of this particular node A, or A is a child of a node B. So this will create a tree for a traversal. Breadth first search algorithm traverses a graph in a level by level ordering, means it will be visiting the vertices of a graph in a level by level sequence. This breadth first search traversal, for implementing this particular technique, we will be using a queue data structure to remember which vertex to be searched next. Okay, so if we take an example, in a graph G, we need to select a vertex as a starting vertex. So I have taken this 0 as a starting vertex. Level means now 0. If we have taken the starting vertex as 0, then this 0 will be present at the root node of a tree, and this will be at the starting level 0. Now the adjacent nodes of this the adjacent node of this vertex 0 will be coming in next level. So the adjacent node of 0 are 1, 4 and 2. So next level, the vertices for next level is 1, 2 and 4. Now next is 2. Why? Because adjacent of 4, 0 is already visited, 1 is already visited, so we have not, and 2 is also visited, so no child of level 4th vertex. For 1, the adjacent vertex of 1 are 0 and 4, which are already visited, so we have not taken any child for 1 as well in a tree. We are only considering the vertex which are not visited yet. Unvisited vertex will be considered. So for vertex 2, we have adjacent of 2 as 0, 4, 9, 10 and 5, in which 9, 10 and 5 were not visited. So next level 3 will be having vertices 5, 9 and 10, and the parent of these will be 2. For 5, the unvisited adjacent vertex of 5 are 6, 7 and 8. So next level, in next level, the vertices are 6, 7 and 8. For 9, the vertex was 11, which was not visited. So now all the vertices of this graph are visited. So this is the breadth first search spanning tree. And the traversal of this tree is done from the starting 0. Next level is 1 to 4, so 1 to 4 will be visited. Next level are 5, 9, 10, then 5, 9, 10 will be visited. Next level is 6, 7, 8, 11, so 6, 7, 8, 11 will be visited. So breadth first traversal will be 0, 1, 2, 4, 5, 9, 10, 6, 7, 8, 11. There can be more than one breadth first search traversal as the sequence can be, because there is no particular sequence based on the starting vertex 0. Next unvisited vertices of next level was 1, 2 and 4. So we can we can traverse this vertex 1, 2, 4 in any sequence. We can take 2 first, then 1, then 4, or we can take 4, 1, 2 or 4, 2, 1, any of the sequence. So based on this, There can be more than one breadth first search traversal. Let's study the breadth first search algorithm to have a clear view of how this breadth first search is being how breadth first search is traversing every vertex of the graph. We will be having a queue data structure, and the size of the queue will be the total number of vertices which is present in the graph. Then we will be selecting any vertex as a starting point for the traversal, because we need to have one of the starting vertex, so we can select any of the vertex as a starting point for the traversal. We will be visiting that particular vertex. As we are starting from that vertex, we have visited that vertex, and we will insert that vertex into the queue by enqueue operation. Now next will be, until the queue is empty, we will be visiting all the non-adjacent vertices of this particular vertex which is at the front of the queue, and we will insert them into the queue. Okay, so next what we will be doing is, the vertex which we have inserted in the queue, we will be taking that vertex, and we will be the vertex which we will be taking from the front size of the queue. Okay, and like in queue data structure, always deletion is done from the front end, insertion is done from the rear end. You are well aware of a queue data structure. So whenever we will be performing the traversal, what we will be doing, we will be deleting one element, one vertex from the queue, from the front end, and we will be finding the non visited adjacent vertex of this particular vertex, and all the adjacent non visited vertices will be inserted in the queue from the rear end. Okay, which vertices? Which are non-visited adjacent vertices of the vertex which was deleted from the queue. When there is no new vertex to be visited from the vertex which is at the front of the queue, then we will be deleting that vertex. We will be repeating this step 3 and 4 until the queue become empty, and when the queue become empty, then we will produce a final spanning tree by removing the unused edges of the graph. Let's take an example and understand this particular algorithm. We have considered this particular graph for the breadth first search traversal. We have selected the vertex A as a starting point of the visit array visited, as we have taken the starting vertex A as this particular. So we have made this visited A as true. For visited, we can take an array, and the size of this visited array will be the same as the number of vertices present in the graph. For visited and unvisited, to discriminate which vertex is visited and which is unvisited, we can take, initially all the vertices are unvisited, so we have taken all the values of visited array as 0. Okay, now as the vertex will be visited by that particular index number of a vertex, we will make that vertex as 1. One will denote, represent that particular vertex is visited, and if it has a value as 0, that means it is not visited. So the starting vertex, we are starting from a particular vertex, we will be making it visited as 1, visit true, and we will be inserting it from in the queue. Insertion is done from the rear end. As the queue was empty, A is the first vertex which is inserted in the queue. Now we will visit all the adjacent vertices of A which are not visited. Adjacent vertex of A are B, D and E which were not visited. So we will be inserting these newly visited vertices into the queue. B, D, E or D, E, B we have inserted in the queue, and then we have deleted A from the queue. Okay, now A is visited, we have print A, traversed A, print A, and inserted these unvisited vertices into the queue D, E, B. Now next, as in front the vertex is D. Okay, we have inserted D first, so vertex is D. So now we will be visiting all the adjacent vertex of D which are not visited. So adjacent vertex of D are A and V, both are visited, both are present in the queue, both are visited, so there is no vertex, so we will be deleting D from the queue. Next element is E at the front. So we will be visiting all the adjacent vertices of E which are not visited yet. So C and F are the vertices which were not visited. So we have made them visited and inserted in the queue. C and F are inserted in the queue, and we have deleted E from the queue. Next is B. Now we will find all the adjacent vertex of B which are not visited, but all the adjacent vertex of B are already visited. There is no such vertex. So now we will delete B from the queue. Next is C. Now we will find all the adjacent vertex of C which are not visited. Only G is there. We have made G as newly visited vertex and inserted into the queue and deleted C from the queue. Next is F. Now we will be finding all the adjacent vertex of V which are not visited, but all the vertices of edge which are adjacent to F are visited. So there is no such vertex. We will be deleting F from the queue. Next is G. We will be finding all the vertices which are adjacent to G which are not visited, but there is no such vertex present in the graph which are not yet visited. So we will delete G from the queue. Now Q becomes empty. So we will be stopping breadth first search process, and the final result for the breadth first search is a spanning tree as shown. A is first, then D, E, B, then C, F, then G. And the breadth first search traversal will be A, B, A, D, the sequence in which we have deleted the vertices. First we have deleted A, then we have deleted D, then we have deleted E, then we have deleted B, then we have deleted C, then deleted F, then we have deleted G. The sequence in which the vertices were deleted is the sequence of a breadth first search traversal. Now there can be more than one breadth first search traversal. How? Based on this spanning tree also we can find more than one breadth first search traversal as A. Next level is B, D, E, B. So first we have taken D, but we can also take B also as a first. So A, B. If you are taking B, you need to store all the elements. If you are taking A, B, E, D, if you have stored in a queue B, E, D, then next you have to take the adjacent of B. Remember the sequence in which you are inserting in a queue. You have to take the adjacent vertices from that sequence only, because deletion is always will be done from the front end. Okay, there can be more than one breadth first search traversal, but you have to make sure that the way in which they were inserted in the queue, vertices were adjacent vertices were inserted in the queue, will then that sequence will be the sequence in which you will be taking the adjacent vertices of these adjacent vertices. Okay, like we have explained in the pseudocode also. For breadth first search, input will be the graph G. You can also have the starting vertex as an input in a graph G. We will be taking Q. The size of this particular Q will be the same as the number of vertices present in the graph. Then for visited, you can take a visited array. The size of the this particular visited array will be the same as the number of vertices present in the graph. Some integer variables will be required for storing the current vertex. While G has unvisited node X, the starting vertex, we will visit that particular starting vertex. We will insert that particular starting vertex into Q. X is the starting vertex for the traversal. While Q is not empty, we will be deleting one vertex from Q. Deletion will be done from the front end, and we will be visiting all the unvisited neighbor of this particular Z. Unvisited neighbor, unvisited vertices of this particular node Z, and we will make all those unvisited vertices as visited, and we will insert them in a queue. The sequence they will be inserted in the queue will be the sequence they will be deleted from the queue. So make sure the deletion, based on the deletion, if they are deleted, then their adjacent vertex are inserted in the queue. So you have to make sure of the sequence for the breadth first search traversal. This is the breadth first search traversal technique. The key points for breadth first search traversal are: first is that breadth first search traversal is using queue data structure, and next, the size of this particular queue data structure will be the maximum size will be the total number of vertices present in the graph. The total time complexity for visiting for implementing for this particular breadth first search traversal will be big O of V plus E, where V is the number of vertices and E is the total number of edges. Okay, So this is a breadth first search technique, and we can have more than one breadth first search traversal for a given graph only based on which particular vertex you have taken first. If there are more than one adjacent vertex, and which particular vertex you are considering first, on the basis of this there can be more than one breadth first search traversal. It can also be depending that which particular vertex you have taken a starting vertex. Based on the starting vertex also, there can be more than one breadth first search traversal. Thank you.